let's begin. I can't believe this is the last week of class. And actually, this is the last week that I'll be teaching this course. It gives me, my heart is kind of racing. I've taught this 7 years now. We'll talk about it on Thursday a little bit. Over, 700 students or so. I'm like, hey, here you go, take the course. It's mine. And so that's how I feel about it. But I think it's good to pass it on to someone else. So you need fresh blood. But I'll catch you in statistics. So, I'm not going away. Make sure you take note of this calendar. Today we're on the 3rd. I want to finish with differential equations. I think we can finish off today with boundary value problems and just be ready for the exam. On Thursday, you really need to come. If you haven't attended Professor Saad's end of class events, you should. Well, you obviously haven't attended because this is kind of the first time you see me. So you should. There will be pizza. We're going to be having some fun time. We'll do some student awards. Thank you for those who submitted nominations. You'll get a certificate that you can hang on your wall, stamped University of Utah stuff. And I just ordered 3D printed lobsters, so you'll get those. Put them on your desk or a keychain or something. And we'll have a fun time. We'll talk about the course a little bit. Then I give this thing called Manifesto for Life. It's the story of my life, so you get to answer all your questions: where I'm from, why do I have no hair, when did I lose my hair, do I have a picture with me with hair, where do I buy my clothes, stuff like that. And then you get to ask me anything you want anonymously, so we'll have a Google chat, and you can go in and you'll ask whatever you want, and I will not be offended. I don't have to answer all questions. But you can ask me literally anything anonymously, or your account doesn't matter. However, throughout this, from now until the exam, obviously I want to be available for you for help as you prep for the exam. And Lillian and Davin just came up to me and told me they want to have office hours also for you guys. So they will figure out a time where they can do that that's most effective for you. So you can continue reaching out to me and them through Canvas over the weekend. I'll take the lead on those over the weekend. Monday I'll have, if my door is open, just come on in and talk to me. But I'll have a office hours from 1 to 2 for sure. And then Tuesday is the final exam. I sent you the study guide, information about the exam, etc. So it will be a handwritten type. You'll get 2 to 3 problems on ODEs and 1 to 2 problems on regression. Most likely it's going to be 3 problems on ODEs, 1 problem on regression, and 1 problem like general questions. So you don't have to really revise everything in the course, but know that in the ODE problem there will be a nonlinear ODE problem. You need to remember how to do Newton's method. So I'm trying to kind of simplify it as much as I can for you. Definitely focus on ordinary differential equations. You'll get 2 cheat sheets, double-sided. The exam is from 1 to 3 p.m. over here. One more thing. For Thursday, you will get to do your, I'll ask you to do your student feedback, and I will count that as an assignment. But you have to come in person in class, so I'll have a code that you have to put in to access the assignment. What you'll do, you'll go submit your evaluation and then take a screenshot that says, okay, yes, I've finished evaluation, and you upload that to the assignment, and you'll automatically get credit. It will count as 1 homework, okay? It will count as 1 homework assignment. So, this is a low bar to pass. Just come here. I want you to be here, have a good time, do the evaluations. If you already submitted your evaluations, thank you. You'll get a chance to upload the screenshot of the confirmation that you did the evaluation, okay? And then that's it. I'll see you then in statistics in the spring, okay? So let's, yes?
Wait, so when you say that it covers 1 homework, is it like extra credit? Or is
it will count as 1 homework assignment. So you'll get 100% on that. 2 homeworks dropped, so you'll get the 2 lowest homeworks dropped. So it's a good deal, right? A Black Friday deal, okay? All right, so let's continue this. Let's finish off and put the final nail in the coffin for differential equations. We did initial value problems. Now you're experts in initial value problems. You understand how we do the forward Euler and the backward Euler method, so explicit, implicit. Now we're going to go back to the second type of differential equations, which are boundary value problems, where the initial condition doesn't matter, really. It's the boundary conditions that matter. And guess what? We did that problem at the beginning of class in September. We did that when we looked at the heated rod. We had this heated rod, temperatures fixed at both ends. And what happens to the heat inside the rod? You know, it's being heated by a fan or something, or cooled by a fan, you know, but it's the boundary conditions that matter in that problem. So we're going to look at these types of problems. So typically, any boundary value problem is a problem that has boundary conditions. When it comes to ODEs, when you see d by dx or d by dy or d by dz, those are the typical symbols used for spatial coordinates. You immediately recognize that this is a boundary value problem. Now, partial differential equations, they combine initial value problems and boundary value problems together. So you get time and space, you get a partial differential equation, okay? But in this class, we separated them. We did initial value problems separately, and boundary value problems, we're going to do that separately, okay? A typical example is the one we already did, and that's the heated rod. So this is nice because we already saw this problem. You might not remember it. That's okay. We'll remember it together. But a classic example of boundary value problems is heat transfer. And you'll learn next year about heat transfer, where to get this equation from. Don't worry about it right now, but you have to trust me that this is a true equation for heat transfer. I'm teaching you the tools here to solve it. So next year, when you learn how to derive this equation, and you already have the tools to solve it, so you'll get the full education about it. This describes the change in temperature, defined by the symbol T up there, in space x along the rod. The rod is fixed, has fixed temperatures on both ends. There's T on the left side and T on the right side. Later, we will learn that we call these Dirichlet boundary conditions, but for now, don't worry about that terminology. So we have fixed temperatures at both ends. That immediately tells you this is a boundary value problem. On the right-hand side is the thing that influences this second derivative for temperature. It so happens that heat can be described, heat transfer can be described by a second derivative. And you will learn that diffusion and mass transfer also behave the same way. They're the same thing. How mass is being transferred, how heat is being transferred, diffusion, concentration diffusion, they all obey a second derivative. On the right-hand side is what is driving the heat transfer. In this case, there is air that is blowing at the rod, okay, at some temperature T infinity. So we did this problem in one of the homework assignments. You could have radiation over here. So we'll have another example later where you could have radiation that is driving the heat transfer on the rod itself. But the equation, the second derivative is not going to change, only the right-hand side will change. Okay? So this is an example of a boundary value problem. Now, the unfortunate thing about boundary value problems, in almost everything that we did in class, if you remember, everything we did in class, we learned one way to do it with a built-in Python function or routine, like fsolve, linalgebra.solve, polyfit, curvefit, ODE-int, right? So we had a tool that is built in Python for everything that we did, quad, scipy.integrate.quad, right? And trapz, numpy.trapz. All of those, we had a tool in Python, and then we did our own implementation to compare, right? Except for boundary value problems, okay? Except for boundary value problems. It is the only type of problem where there's not an effective tool in Python to solve it. So you have to come up with the solution strategy yourself, and it will be different for each problem. Now, I am partially correct. I'm not trying to do disinformation here, but there is one tool that only works in a very limited case for boundary value problems, and that's why I don't teach it. And so, but I have to cover it. So that tool is from SciPy. It's called Solve Boundary Value Problem, Solve BVP. Okay, we're not going to cover it this year because it's not very robust. Solve BVP is a routine that only works for one-dimensional boundary value problems. It is incredibly cumbersome to use, so that's why I don't teach it, and it's not effective. It's almost always easier to derive the governing, to discretize the equation, turn them into algebraic equations like we did in September, than to use solve BVP. But I wanted to put it out there, so you know next year if somebody tells you, oh, you didn't learn about solve BVP, you tell them, we did, but it's not robust. It's a crappy tool. Let me show you how to solve this problem, okay? We come up with that, that attitude. Okay. Now, the more effective strategy to solve boundary value problems is for you to actually build the solution yourself using using the finite difference method. Now, finite difference, we learned, finite difference methods are ways to approximate derivatives, right? Previously, we had the function or we had the data. We computed the derivative from those data. Here, with differential equations like we did with initial value problems, we're going to approximate the derivatives with the finite difference, but we don't know the value, but we're going to use that to get the values. So here's how it's done. We're going to consider the same problem, the heat transfer in a rod. We'll do another example later, but just we start with this one because we've seen it. Second derivative of temperature, there's this HP over lambda AC times T minus T infinity. So I'm going to call that entire parameter, I'm just going to call it H for simplicity. This is just a number, okay? It's just a number, all right? This is just a number. So we have second T double prime equal H times T minus T infinity. We have a fixed temperature on the left, we're going to call it T left, and a fixed temperature on the right, T right, okay? Now, based on what we did with initial value problems, what is the first step in solving this numerically? So if you remember in time, when we were solving the initial value problems, we said we're going to take the time domain and split it into small intervals, right? We're going to do the same thing here. We're going to take that rod, which is our domain. That's where we're trying to find the temperature. And we're going to split it into equally spaced points. We did this in September, right? So we're revisiting that, but with more knowledge right now, okay? Now, the distance between those points could be fixed or not fixed. It's easier to deal with the fixed. Most cases, we can do it with fixed spacing. The extension to unfixed spacing is not that complicated, but we don't need to cover that here. It's rarely used in what we're doing. So we're going to divide this into n equally spaced points. So you could say I want 100 points, so that gives you n minus 1 intervals, for example, right? The spacing, we call that delta x, and we're going to assign a coordinate to each point. We start at x0, x equals 0, x2 is x1 plus delta x, x3 is x2 plus delta x, and so on all the way to xn. So we have n of these points, and xn is at L. Okay, good. So now we have the discrete spatial coordinates. Next, we're going to assign, this is exactly this, these are the slides exactly from September. Okay, I'm just copying them back here, okay? And we're going to assign a temperature at each one of those points, because numerically we cannot solve, like we do analytically by hand, we cannot solve this equation at all points on the rod. We're going to only be able to solve it at those discrete points. So the next step is to assign a variable at each one of those points. We start with T1, which we know. That's given to us by the problem definition. And you typically know this. Say you're studying the heat transfer in this wall. You can measure the temperature on this side, measure the temperature on the other side, look at what's inside the material, and then see how the temperature is changing inside. So typically you know the temperature at both ends, so that's given to you. And then we put T2, T3, all the way to Tn minus 1, and then Tn is also given to us as T right. So, you know, it could be 200 and 500 kelvins, right? Or 300 and 400. Those are given to you, but we don't know the points in the middle. But I'm going to give them names because I'm trying to solve for them, all right? I'm trying to solve for them. Okay. Now the next question is this equation valid at these discrete points? Is this ODE valid at all of these points? The ODE is valid on the entire rod. So wouldn't it be valid at those points? Yes, like we did with initial value problems. So I can take that ODE and indeed apply it here. I can say that d2t by dx t double prime at point 2 is equal to h times t2 minus t infinity. Agreed? So I'm applying that differential equation at each one of those points. So it's valid here, it's valid here. It's valid at any point inside that rod. At the end points, I don't need it because I have the temperature, right? So I already have a value for the temperature, so I don't need to solve that equation over there. But at all the interior points, this ODE is valid, and that's what I'm going to use to find a relation between all of those unknowns so that I can solve for them, all right? So we're going to pick a representative point, I. When we were doing initial value problems, our representative point was n, right? So we applied the differential equation at some arbitrary point n. Here we applied at some arbitrary point I. This is just a common convention in this kind of analysis. Okay. So now, what do you think is the next step to convert this at each one of those points, to convert it to a relation between the points? Now, I know you probably still you haven't reviewed your initial value problem, so I'm going to help you a little bit here. Okay? What did we do with the initial value problem for the time derivative? So the only issue here is this derivative, right? We don't know what it is. But we have ti, which we're going to solve for, but the second derivative, we don't know how to evaluate it. We don't know. We need to convert that second derivative into a relation between ti minus 1, ti plus 1, ti, etc. Right? So the next step would be to approximate this derivative using a finite difference formula. So the problem here, again, we're trying to find a relation between t2, t3, t4, t5, and so on, or a bunch of relations. Okay? So how many unknowns do we have? N minus 2 unknowns. We need n minus 2 equations. Where do I get those equations from? I'm going to get them from the differential equation itself. But the differential equation has a second derivative. It doesn't have ti and ti minus 1 on the right-hand side. Sure, it does. But here, I need to convert this to something that contains ti, ti minus 1, ti plus 1, and so on. Right? So the best thing to do is to do a finite difference formula and see what happens. So here, this is where your knowledge of finite differencing comes in. And so if we take the second derivative and you remember the central difference formula for a second derivative, you might not remember it. That's why I had look at your notes. So I'll give it to you also in the exam, by the way. So if you take this second derivative and I approximate it with a finite difference formula, bingo. You got a relation, an algebraic relation between point I plus 1, and I minus 1. For this approximation, you could have used a fourth order central difference. It will give you a different relation between different points, but the point I'm driving here is that you've converted the differential equation with derivatives into an algebraic relation that has the ti's in it. Okay? Now I is an arbitrary point, so you can apply it anywhere. You can apply this equation anywhere. But first we simplify it. So I want to bring all the unknowns to the left-hand side and everything I know to the right-hand side. Because guess what? This is a linear equation in the unknowns, right? All the unknowns ti minus 1, ti plus 1, they show up linearly. So if I multiply by delta x squared and place the unknowns on the left-hand side, I can write this in a standard form for doing system of equations. Okay, so now we have all the ingredients, I claim, to solve this problem. All right, so now it's a chance for you to tell me what to do next. Elijah? Okay, so reorganize what into a matrix? Okay, Ashton? Same thing. So mechanistically, you take this equation, and at I equal 1, we already have T1. It's given to us, right? At I equal 2, you just put I equal 2, and you get a relation between T1, T2, and T3. At I equal 3, you get a relation between T2, T3, and T4, and so on and so forth. So you take this generic formula, okay, and apply it at all of those points. And you're going to get one equation for each point that relates the different points to each other, right? So here's how you do it. At point I equal 1, you already have T1 is equal to T left. That's given to you. At point 2, you have the formula. Put I equal 2 in the formula. What do you get? T1 minus 2 plus h delta x squared times t2 because I equal 2 plus t3 equal minus h delta x squared t infinity, right? Like couldn't be easier, right? At point I equal 3, you get an equation. And at point I n minus 1, you get that. And the last point is given to you, Tn is equal to T right. Okay? So now what is this? What are your unknowns? They're T2, T3, T4, T5, T6, etc. Do they show up linearly or non-linearly? They all show up linearly. This is a system of linear equations. Again, that's why we study linear equations at the beginning. A system of linear equations. How do we write it? We put it in matrix form. So you convert this, you have all the equations. Now, this seems tautological, like Tn equal T right, T1 equal T left. Do you need to include it in your system of equations? You don't have to. But I like to include it so that my solution contains the endpoints as well when I'm plotting. Okay? So in matrix form, this looks like this. And guess what? This is a tridiagonal system of equations. You have the left-hand side and the right-hand side. You put the matrix form, you get the unknowns, and we know how to solve this. We did it. The only missing link that I promise I will teach you how to do is that finite difference approximation. That's it, which you already know how to do. There's really nothing magical going on here. This is easier than the initial value problems, right? Because with the initial value problems, we had to make that jump of converting the derivative to an approximation, but here you just know how to do that similarly, and you just have to solve this system of equations. Now, this could change a lot, so you'd have to redo this every time you're presented with a different problem, okay? So we're going to do this to refresh your mind. We're going to do this in Python again. And remember, we built this coefficient matrix using the diagonals, main diagonal, upper diagonal, lower diagonal, and building the right-hand side and pushing this through numpy.lin algebra solve. Okay, so let's do this in Python now. Get a notebook up and running. Bless you. Okay. Solving differential equations. All right. So, you know, this is not the first time we do this. You can review previous lectures if you're kind of a little bit rusty, or just kind of follow with me here. So I'm going to import. First, I'm going to call it in class BVP with Dirichlet conditions fall 2024. So I'm going to import numpy as MP because I need lin algebra.solve, okay? And I need to import the magic as well. Well, maybe not the magic, hold on. Let me see where I can. Okay. So I'm going to import the copy and paste the Python, the matplotlib magic. All right. That's all I need for this, really. All right. So for this problem, again, we're going to define the number of points, not the intervals. So let's do 100 points. We can change that later. x0 is equal to 0, and L is equal to 1 meter. Okay. And then left temperature, let's say, is 100 kelvins, and right temperature is 300, and T infinity is 500. So we are heating the rod. Let me get the slides so I know what I'm doing. Okay. So this is my problem set up here. Hold on. Okay, so I got T left, T right, and I need T infinity, right, for this problem. And that parameter h is just a bunch of parameters that contain heat transfer coefficient, etc. So we can call h, say, equal to 10. So it contains the heat transfer coefficient, perimeter, and the area, all that information, right? Now we create a lint space like we did, usually, just for plotting purposes. So x0 to L with endpoints. And then I'm going to need delta x. If you remember, we have delta x squared here, delta x squared here. So I need delta x. I'll do simplest way is to do x1 minus x0 from the array. So that gives you delta x. Okay. And now I can build my diagonals. Lower diagonal is all ones except the last entry. Upper diagonal is all ones except the first entry, which is 0. The main diagonal, it's all minus 2 plus h delta x squared except the first and last entries, right? So we start with the lower diagonal is mp dot ones. What is the size? N minus 1, because I have n, a matrix of size n by n. I have n equations and n unknowns. Agreed? So the main diagonal is, has length n. The first lower has length n minus 1. And the last entry in the lower diagonal is 0. So I can put LD minus 1 equals 0. And then the upper diagonal is also mp dot ones of size n minus 1. And the upper diagonal, the first entry in the upper diagonal is 0. Right? So just look at that matrix. The first entry is 0. And finally, the main diagonal is minus 2.0 plus h times dx times dx times mp dot ones of size n. That gives me the main diagonal. I need to fix the first and last entries. So md0 is 1, and md minus 1 is 1. Okay? And, you know, if you're in doubt, print it, but print it out for like 5 points, just to see how it looks like. You can print it now, or we print it after we build the coefficient matrix. So we finally built the coefficient matrix using the diag routine, if you don't remember that. So that will take an array, a one-dimensional array, put it on a diagonal in a full-size matrix. Okay? So mp.diag, for the lower diagonal, it's located at minus 1. For the main diagonal, is located at 0, at index 0, plus mp.diag. For the upper diagonal, located as 1. If you have no idea what I'm doing here, that's a problem. Print A. So now, okay, there you go. So at least it looks right. On the first lower, I have 1, 1, 1, and 0, just like I expect there. On the main diagonal, I have 1, and then something, 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 and then 1, which is what I expect there. On the upper diagonal, I have 0, then 1, 1, 1, which is also what I expect. So at least it looks correct. You could have a mistake in the number here, but at least the structure of your matrix is correct. Okay? All right. Okay, almost done. We need the right-hand side now. Let's do the right-hand side is equal to, we have minus h delta x squared times t infinity. So I have minus h times dx times dx times t infinity times mp dot ones of size n. And I need to fix the first entry in the right-hand side is going to be to t left, and the last entry in the right-hand side, and that's going to be t right. Agreed? So that's an array. And you can print the right-hand side. Indeed, the first entry is 100, which is the temperature on the left. The last entry is 300, which is the temperature on the right. And you get this minus h delta x squared in the middle. And that's it. So now we can solve it. Let's put more points. Let's put maybe 100 points. And now I can do solution is mp.lin algebra.solve. And what does it need? A and the right-hand side. That gives me a solution. What do I do with it? When data is spotted, it better be plotted. So let's plot it. plt.plot. We're going to plot the solution versus the x-coordinate. And my solution contains the temperature. Okay. And look at that. So let me fix this a little bit over here. Put a grid. PLT. Nothing new here, seriously. We did this numerous times before. We played around with the temperature. We played around with H, with T infinity, etc. That should be an easy problem, a familiar problem at least for you. You can review it. We've done it before. You did the homework. You nailed the homework. So this shouldn't be new territory for you. Okay? What's going to be new territory is what's going to come next. And we're going to talk about ghosts. Ooh. Do you believe in ghosts? Yes? Good, man. In aliens. Do you believe in well, whether you believe in them or not doesn't matter, right? But why haven't we been contacted by aliens yet, Zach? Or are they here amongst us? Okay. So I'll leave this up for a second. You got it? Oh, scroll down. Here? Okay, leave this up here for a second before we talk about ghosts. Actually, that would be a good thing to do a t-shirt about the ghost point. I had a student in my graduate computational fluid dynamics course I taught in the summer. We were doing these project presentations, and we have, we solve problems like this, but in 3 dimensions. So we have very complicated grids to look at, and like we put temperature on one point, we put the velocities on other points. So it's very complicated. So in her project, everybody was using the standard color theme, etc. But she came in and put like this purple, pink, very, very beautiful theme. Told her you're gonna feminize the CFD. I told her it would be cool if you do a sweater out of this. And we laughed about it. So she sends me an email about a month ago. She actually crocheted a sweater with the staggered grid. We call that the staggered grid, with the staggered grid on it. And it looked so cool. I was like, can you make more of these so we can pass them? She said it took me like 100 hours just to make that one thing. So anyway, that was fun. If I have a minute at the end of the lecture, I'll show you the picture of the sweater. Okay. All right. So okay, good. So we did this. There's something we need to talk about though, and that's boundary conditions. Boundary value problems deal with boundaries, so it's important to talk about what kind of boundary conditions we can apply. So far, we only applied a fixed fixed value at the boundary, t left and t right. It's cool standing here, actually. Kind of like forces everyone to look at me. Kind of good exercise. Feel like you get sore just looking on one side. But I need a clicker for this. So we need to talk about boundary conditions. So far, we covered only one type of boundary condition, and we call that a Dirichlet boundary condition. When the value of the dependent variable in your differential equation is specified at the boundary, we call that Dirichlet boundary conditions. A guy, his last name was Dirichlet, and he was like, I claim this type of boundary condition under my name, and everybody calls it Dirichlet boundary condition, or fixed value boundary condition. Okay? For simplicity, Dirichlet, fixed value boundary condition. So value on the one end is fixed, the value on the other end is fixed. Or any value that's fixed, that's called a Dirichlet boundary condition. But that's not the only type of boundary condition you can apply. You can also apply a rate at the boundary. So sometimes it's really hard in these problems with heat transfer to actually set the temperature. Typically, what you will have is a heating rate at the end of the wall or the rod or spatula or whatever. So in that sense, you can't set the temperature, but you can set the rate of heat transfer at the end, the rate of mass transfer. And that can be applied as a boundary condition, and that is called a Neumann boundary condition, when you specify the derivative or the rate of the dependent variable at the boundary. So this is new. We haven't seen this before. So instead of specifying a fixed value at the boundary, you specify the derivative, a rate at the boundary. So say d phi by dx at the left is beta, some number. D phi by dx on the right is some other number. Okay? So that specifies the rate, in this case, the rate of heat being transferred or withdrawn out of the system. Okay? These are more natural because they're more practical to implement in experiments than setting a fixed temperature. Now, with a boundary condition like this, you don't know what the value of phi is. All you know is the rate at the boundary, okay, the slope. So if you have a positive slope, your phi is going to change so that the slope is pointing up. If you have a negative slope, it's going to point down. If you have 0, it's going to be flat. So that's what we're going to use to verify our calculation. Okay? Now, you might mix them. You might, on the left-hand side, you might have a Dirichlet condition, and on the right-hand side, you might have a Neumann condition. So you can use them interchangeably, the words as well. Dirichlet or fixed value, Neumann or derivative condition. Okay? Neumann boundary conditions, however, in practice, they pose a bigger problem than we've seen so far. So we're going to consider that same example we did before. Second derivative, heat transfer with in the rod, and there's cooling or heating of the rod, T infinity. Except now, in this case, I'm fixing the temperature on the left. So I have a Dirichlet boundary condition on the left, but on the right, I have a Neumann boundary condition. I can swap them, it doesn't matter. I can put Neumann conditions on both ends, it doesn't matter. Okay? Just an example. Okay. So now we have a problem because we really don't have an equation for Tn. Previously, the last point, we had an equation for Tn. Tn was equal to T right, the value that was specified to us. Right now, we don't. We only have the slope at the end point. So we need to do a couple of extra steps to extract a relation for that temperature at the end. Okay? So, however, our discretized equation is still valid at the end point. Okay? So we're going to use that to our advantage. So what we're going to do, we're going to take that discrete equation and apply it at point n. So you get Tn minus 1 minus this guy times Tn. Okay, good. So now Tn is showing up. But we've introduced a new unknown called Tn plus 1. There's no Tn plus 1 because that's outside our computational domain. As far as I know, that's vacuum, or there's a black hole over there. I don't know. So really, Tn plus 1 doesn't exist. Yet, if you write the equation, it forces you to have a Tn plus 1 showing up over there. So we imagine that there is a ghost. Okay, that's where the ghost comes in. Okay, it's a ghost point. That there's a ghost point, literally, that's what we call it. We call it a ghost point. It's really only a mathematical trick, intermediate trick, just to allow the math to work, and then we're never going to use that ghost point. So imagine for a minute now, there's a ghost sitting there called Tn plus 1. Okay? But I don't want to add an equation for Tn plus 1 because Tn plus 1 doesn't exist really. Okay? But there's still one equation that I haven't used to eliminate Tn plus 1, and that's the equation of the boundary condition. So now we need to eliminate that ghost point, and we can accomplish this by using the derivative at point n. What do? We discretize the derivative. If I discretize the derivative with a central scheme for dt by dx at n, that's Tn plus 1 minus Tn minus 1 over 2 delta x equal beta. Okay, so now see what happens. I related Tn plus 1 to Tn minus 1 in this equation, And I can use this now to eliminate Tn plus 1 up there. So if I take this Tn plus 1 and plug it in here, if I take this Tn plus 1 and put it in there, there's no more Tn plus 1. It becomes only in terms of beta and Tn minus 1, right? So no more ghost point. So the ghost point, we used it only as an intermediate step, and it was cool also to say that there's a ghost out there and stuff, right? But it doesn't exist, okay? Pretend it doesn't exist. So now when you substitute it, you rearrange the equation, you still get an algebraic equation at the last point, but it looks very different than what we did previously. Previously, the equation at point n was Tn equal the boundary value. Right now, just because we put a Neumann condition, we get a completely different equation at the end point. Okay, 2Tn minus 1, minus 2, etc. You have to do the algebra every time. Each problem is going to be different. Don't memorize this equation. Learn the technique of how to get this, because I can change this in 1,000 ways. And each way, you're going to get a different system of equations. So you have to learn the procedure, okay, how to do it. So then you write down your equations. You still have a system of linear equations. T1 equal T left. This equation for all points in between from T2 to Tn minus 1, they look like before. The last point is this guy, is this equation. So here's how I would approach it. Like when you're solving this in the exam or in the homework, it's like, okay, what's the equation at the boundary? What's the equation in the middle? And what's the equation at the other boundary? That's it. You have 3 steps to do. The equation in the middle, there's one equation for all of these points. So you apply it, it's a template. So at point 2, point 3, point 4, all the way to point n minus 1, all the interior points if you want. Okay. Then you put this in matrix form, but now see what happens here. This lower diagonal doesn't have a 0 here anymore, it has a 2. This guy, it looks like this guy, and also the right-hand side has changed. Okay, just because of that Neumann boundary condition at the end. Okay, so let's do this. We take that same heated rod problem, but with a Neumann boundary condition on the right-hand side. Okay, so we're going to solve this problem now. In Python. So I'm going to create a new, let's say, new cell. Neumann BCs, boundary conditions. Okay. So I'm going to copy and paste everything because everything looks the same. Okay, over here. Everything is going to look the same. Except for a few things. Except for the last point, really. Okay. So move to Creston. Move here. Okay. So everything looks the same as before. We have on our lower diagonal, we have 1s, except the last entry is 2. Okay, so on the lower diagonal, I have 2 at the last entry. Now, again, I tell you again, when you talk to me in the help session, I tell you, show me your math first. Don't show me the code. I need to see the math because the code needs to reflect the math. I'm looking at the math here to guide my coding. What I'm implementing should be consistent with my math derivation. I got on my lower diagonal 1s, except the last entry is 2. I'm going to change that to 2. On the upper diagonal, I have 1s, except the first entry is 0. So that's still valid here. On the main diagonal, I have minus 2 plus h delta x squared everywhere, except the first entry, it's 1. But the last entry is still the same, so I'm not going to touch the last entry. I'm going to delete that. Agreed? Okay. And that's enough to build that coefficient matrix. So let's do it for 5 points and print it. So I'm going to comment all of these guys out. Oh, I don't need to comment them out. Okay. Okay, so good. So I got 1, 1, 1 on the lower diagonal, and then 2, what I expect. 1, and then the same number. Look at this, minus 2.6, minus 2.65, minus 2.625. It's the same. And then 0, 1, 1, exactly as I would expect up there. Okay, very good. Now let's do the right-hand side. The right-hand side is the same, except, So T left and then minus h delta x squared, etc. Except the last entry, it's minus h delta x squared T infinity minus 2 beta delta x. This is where the beta comes in, right? That slope at the end, okay? That slope at the end. So what I'm going to do here, I already have minus h delta x squared T infinity on my right-hand side. So the last entry, I need to reduce it by 2 beta times beta, and we'll define beta in a second, times dx. So see what I did? In my right-hand side, I already have minus h delta x squared T infinity. So I need to subtract from that at the last point. I need to subtract from it 2 beta delta x. So I put minus equal 2 beta delta x, okay? Now you can print the right-hand side. And what? Oh, I don't have beta defined. So let's define beta. Beta is the slope at the endpoint. So let's say, 10, okay? Right, so I got 100 T left, minus 312, minus 312, and this last number is different than this one, okay? If beta is 0, this last number would be the same as this one, so you can check that as well, okay? And that's it. So now we can solve this. I'm going to copy and paste. Yes. Oh, I thought I heard my name. Okay. And then plt.plot, x and sol, then plt.grid. Okay, so I'm doing it for 5 points. Let's make it for 100 points. Okay. I'm going to delete those print statements, comment them out. Okay. Looks like it's going somewhere. It's not a fixed temperature, but that slope at that point over here, that slope at that endpoint should be exactly 10. Now, how can we test that? You can go in the numbers and do a derivative approximation and see if you get 10, a finite difference approximation. Or you can do a quick sanity check. So what I'm going to do is say if beta is 0, then there should be no slope, right? It's going to go flat. dt by dx equals 0. So the rate of change of temperature at the end point is 0. So the temperature profile should go flat. Whatever it's doing in the middle, it's going to be forced to go flat at the end. Okay? Indeed, it looks like, yep, it looks like it's going. It's just at this point here, at least it's not going up, it's not going down. Okay, another test I could do is put a high positive value. So if I put 500, so that's a positive slope, so it needs to be going up. Agreed? So let's test that. That's a good thing, right? So it is indeed going up. Whatever it's trying, it's forcing the heat, the temperature to go up over here. I can put a negative slope, put minus 500, then it should be going down. And indeed, it's pushing it down. Okay? So that slope, it's dt by dx, it's temperature per length, so Kelvin per meter. So how many temperature points are you dropping for each meter that you take, right? And so that does it, right? Now, notice that the value of the temperature itself depends on the slope and everything else going on in the system, okay? Everything else going on in the system. What if you're cooling it a little bit? So let's say T infinity, not cooling, let's say T infinity is 200. Okay, look at that now. It's really dropping off on the right-hand side. On the left-hand side, still 100, but you're kind of cooling the system now, and it's going down. So it changes things dramatically just by putting a rate instead of a fixed value. Okay? With the rate, you don't know what the temperature is. You have to solve it to find the temperature. Because the temperature is going to depend on what's happening inside the rod, right? You only know the slope. You can only guarantee the slope. that you're getting there. Okay? And frankly, that's it. So I'll have another example here for you. So you will get a problem like this, 100%. I will ask you to show me the equation at the left boundary, show me the equation at the right boundary, show me the equation in the middle. Okay? I can put the Neumann condition on the left and the Dirichlet condition on the right, etc. So here's another example. This is d2u by dx squared equal x squared u. And here I'm putting the Neumann condition on the left. du by dx at x equals 0 is alpha. So I'm going to need a ghost point outside the domain at that point. So if you start by discretizing the equation on any interior point, so you get this, you can discretize it, just apply the finite difference on the second derivative at any point I, so you get that. At the left boundary, I equal 1, you write the discretized equation at the left boundary, assume that there's a point outside. So at the left boundary, I equal 1. So you're going to get a u0 here, u1 and u2, right? u0 doesn't exist. It's a ghost point, but we're going to keep it for a second. We will eliminate it with the Neumann condition. So the Neumann condition, du by dx at x equals 0 is u2 minus u0 over 2 delta x. And I'll give you those formulas. This is the second order central difference for the first derivative. So then you get a formula for u0 in terms of u2 and alpha. Then you take this u0 and plug it in here. And that gives you the equation at the left point. So this is exactly the questions I will ask you. 3 questions for any boundary value problem. And then put them in matrix form. What is the equation at the left boundary? What's the equation at the right boundary? What's the equation in the interior? Okay? If you follow this systematic process, you can apply this to any equation. Minus 2 plus delta x squared, x1 squared, whatever you want. So that's the equation at the left boundary. It's a linear equation in u1 and u2. The interior points, you get that equation. And at the right boundary, you have un equal to beta. That's given to you. Okay? And then you can put those in matrix form. But now the system changes. So see how this method is going to require you to redo this procedure for each and every problem. Because you can change it in a snap. They look all the same in a sense that there's a tridiagonal system. You might have a non-zero value here or a 0 value there, right? Depending on where you put that boundary condition, but the concept is the same. The right-hand side is different here because you get zeros everywhere over here because there's 0 on the right-hand side for this equation, right? Another example is the advection diffusion equation. So this equation has a second derivative and a first derivative. We know how to discretize those because we know the formulas for central difference and for the second derivative central difference and first derivative central difference. And you do the same thing. You split the domain into a discrete number of points. In this case, you have fixed temperatures over here on the left and on the right. There's like tons of ways I can vary this. I can put a Dirichlet here and Neumann there, and Neumann here, a Dirichlet there, 2 Neumann conditions on both of them. So all of those variations. Okay? And then at T1, at point 1, T1 is equal to alpha. At any point in the interior, you just apply your finite difference formulas at point I. So this is the second derivative approximation, central scheme. First derivative approximation, central. I need to be central on both so that I have the same error, order delta x squared. If I go central here and first order here, like forward or backward, then I will drop order because this will commit this would commit a first order error. This is committing a second order error. And your error is bound by the worst error, by the lowest, by the worst order error. Okay, and then you reorganize this. So this used to be an exam problem, actually. So you reorganize this. You put the unknowns on the left-hand side. So remember, u, delta x, and d, these are coefficients given to you. The only unknowns here are ti, ti plus 1, ti minus 1. Okay? You put this, and then you can write it in matrix form. And then finally, the the temperature at the right point is given to you, Tn equal beta. Okay? And you put this in matrix form. And you can solve this. So there's so many examples. I really advise you to redo these 4 examples in class, the one with the heated rod, Dirichlet, Neumann, the last 2 examples. You need to master those. Master the process, okay? Because the exam is going to have a problem similar to this with a little change in it. But if you understand the process is simple. You replace derivatives with finite difference approximations, okay? Now, finally, we put the cream on the cherry on the top of the cream of the cream of the cream, and we get to what we call nonlinear boundary value problems. So far, what we dealt with, after we convert the derivatives to finite difference approximations, we were lucky that the systems of equations we obtained were linear, just because the right-hand side, frankly, was linear. But sometimes your right-hand side could be nonlinear, could have powers in the dependent variable, or sine t, or cosine t. What do you do then? You follow the same procedure. Okay, so you follow the same procedure. You follow the same procedure. You discretize, convert the derivative into a finite difference formula, and apply it at point I. When you apply this at point I, you're going to get ti to the 4 here, to the 4th. But then you get an equation. Okay, you have ti plus 1. It's linear in ti plus 1 linear, but it's nonlinear in ti. So this is going to set the entire system of equations into a nonlinear system of equations. So instead of having a linear equation at each point, now you're going to have a nonlinear equation at each point. Do we know how to solve this? Absolutely. It's a system of nonlinear equations. You just need to write the residual at point I, and then you have a system of residuals, and you solve it like we did before, okay, in the beginning. Now, this used to be, when I teach this in the spring, we typically have 1 extra lecture, so we spend more time on solving this together. What you need to know, though, is how to get these residuals, right? So the process of discretizing the ODE, figuring out it's a linear or nonlinear equation, and if it's linear, write it in matrix form. If it's nonlinear, just tell me what the residuals are. Okay, now a cool thing happens, though, on the left-hand side and on the right-hand side in this case. So on the left, I am given the temperature. T1 is T left. So you could argue that, well, this is a linear equation. Sure, it is a linear equation. What's the residual for a linear equation? A linear equation is a special case of a nonlinear equation. You can totally define a residual. The residual at point 1 is simply T1 minus T left. Move everything to the left-hand side. The residual at the last point, at point n, is Tn minus T right. Even if the equation is linear, that's okay. It's still part of a residual system of equations. Do you have a question, Andrew? Yeah. Okay. Now you can do Neumann on this as well. Again, the same procedure. What you need to take out of this is the process. So as you're studying this, do these examples and get stuck. And there's going to be something like, oh, what am I doing here? Write down those questions, and we'll help you understand the details over there. And 100% of the time, it's not my first rodeo, 100% of the time, you're going to come to me this week and next week and say, okay, I understand this, I don't understand that, and it will take me 1 minute to explain it to you. Okay? Because now you're not focused, you want to, there's so much information going on, you really have to go and do it by hand. It's going to take you a couple of hours. Once you do it a couple of times, you ping me, we'll explain it to you, and then you'll be good to go. But understand the process. Please understand the process, because I can change these problems in so many ways. Don't memorize the equations, memorize the process, understand the process. Turn the ODE into discrete form by applying the finite difference formulas. I might give you different finite difference formulas to apply. Right now here we're doing central. I could give you a third order approximation to apply. You should be able to do that. Okay? And that's it. The rest is a bunch of extra material. You can look at those if you want. You don't have to look at those, but that's it. I got about 20 minutes. So your colleague had a announcement to make.
On Thursday at 4 to 6, there's going to be like a holiday party in the ICC, hosted by SEC and AICG. There's like movies, maybe cookies, pizza. So just come hang out.
But you're gonna be full from eating pizza here, so. Okay, so we'll get pizza. We'll get some vegetarian options as well on Thursday. But please come on Thursday, okay? And this is it. All right. Wow, what a great semester! You guys have so many exams coming up. Crunch time. I can't believe how tight the last week is. I wish they'd give you like one extra week of, like they call it, reading period. It's hardly, like you can't even read a page. Seriously, like if they give you one more week, like do the exams December 17th, for example, right? I'm with you here, and we're trying to make a change, but it's a huge overhaul. But so focus on ODEs, the process of ODEs. Okay, that's going to be the meat of the final exam. The practice exam on Canvas is a great representation of what you will see. It's a handwritten exam, so no essay questions at least. So you get to demonstrate your math skills. The voting I'll either do the voting on Thursday for the student awards, or I'll just do it on Wednesday, so I get a chance. I'll send you a link, so I'll get a chance to print the certificates, and you get to come up here and we'll cheer you on, and you'll get to hold the certificate. We'll take a picture and stuff. But yeah, stay tuned and let me know. And I'm not gonna miss you because I'll see you in the stats. Okay, so hopefully. All right. Thank you, everyone. Thank you. Woo!